polynomial exponential equations.
So let me first thank the Institute of Mathematical Sciences for the invitation. I also thank the organizers for all the work they have done and for the hospitality that I could enjoy the last 2 weeks here. Finally, happy birthday, Ram, and I wish you all the best for the next 60 years. Okay, the topic of my talk are polynomial exponential equations, and as I imagine that at least a certain proportion of the audience is not all that much familiar with the topic, so I will give in the first and maybe longer part of my talk some introduction and theory on the topic, and in the last part I will then talk a little bit about some new results in the context. So what are polynomial exponential equations? So, well, we consider equations of the following type: sum L equals 1 to k, PL of x, alpha L to the x equals 0, to be solved in x equals x1 up to xn in z to the n. And here we suppose that these guys PL of x are polynomials. Oh, by the way, I did say, but we simply suppose that we are working within the complex numbers. Actually, technically it works like that, that if one starts the whole business, one works better with algebraic numbers, but here we do not want to go into details of proofs. Okay, so the PL of x are polynomials, and alpha L of x, that is equal to alpha 1L to the x1 times alpha NL to the xn, where the alpha IL are non-zero complex numbers. Okay, now, so if we call this equation here 1, it is clear that a special and maybe easier case of this equation 1 is the one when we assume that our polynomials are just constants. Okay, in that case, we get the following equation: sum L from 1 up to k, AL alpha L to the x equals 0. We will spend some time to study a little bit the situation in this particular case. Now let's see. This equation 2 is, well, let me put it that way, at least very much related to an equation of the following type. Well, we consider the group G generated by these guys alpha IL, by these elements that make up our alpha L. So this group G obviously is a finitely generated group, so it will have finite rank, and so we might consider the equation sum L from 1 up to k, AL epsilon L equals 0, where now we ask for solutions epsilon L in our group G. Okay, so equations in variables taken from linear equations in variables taken from a finitely generated group are, at least to some extent, under control. In fact, some of you have attended my talk last Thursday, and I've showed there the result that such an equation has only finitely many solutions, and that, well, solutions with the following restriction. Solutions where finitely many non-degenerate solutions. Non-degenerate means that in this sum here no proper subsum vanishes, and clearly enough under solutions we mean the following, that if we have a solution epsilon 1 up to epsilon k all within our group, then also epsilon times epsilon 1 epsilon times epsilon k will be a solution. Now let us check a little bit what is the connection between this equation over our finitely generated group and this exponential equation here where, okay, we have no polynomial involved, so we have a simply exponential equation. So let's see what is somewhat the connection. Well, first of all, let's go back here to the non-degenerate solutions. If we consider an arbitrary solution of this equation, well, it might happen that there are some vanishing subsums. Now, let us write lambda for the set of our subscripts 1 to up to k. And now consider P a partition of lambda, and we write small lambda for the subsets that make up our partition P. So, well, if we call this equation here 3, so a solution of 3 might be also a solution of the following system, say 3p, where we now consider vanishing subsums in here. So we consider the system sum L in small lambda, AL epsilon L equals 0, where now lambda runs through our partition P. Okay, now if we have another partition, say Q, that is a proper refinement of P, then it is clear that any solution of the system 3Q is also a solution of 3P. Now we use the following notation. We write script S of P for the set of solutions of 3p of solutions of 3p which are not solutions of a system, say 3q, for any proper refinement. Q of P. So let's see. That means that for all these short pieces, we can apply the result that I quoted just before. So for each small piece, we have, say, if we have a subset lambda of our partition, we get just, say, for lambda, we get a finite number of non-degenerate solutions. Obviously in SP, the solutions are just non-degenerate solutions of those small pieces, right? So for lambda, say we get C of lambda solutions. So these solutions are of the type epsilon L super I, where we say that L now runs through lambda, and as we said that we find finitely many solutions, so we can say so I runs between 1 and C of lambda. So this would be an enumeration of representatives of the solutions in corresponding just to such a small piece. Okay. So that's what we can say for this equation over our finitely generated group. Now it is clear that if we go back to equation 2, for different x's, we might arrive to the same guy here within our finitely generated group. There might be exponents x1 and x2 that lead to the same representative here. Well, let us check that in detail. So, let's see, we have a solution x of 2. The solution x of 2. Okay, now I say, okay, I might introduce the same way as I did it for the equation over finitely generated group. This set S of P. So suppose that X belongs to S of P. I define that in complete analogy without now formulating it in detail, right? So what can we say then okay, so we have done our elements alpha L of X. How does that look like? Well, within our short subset lambda, it will correspond to some of these epsilon L over I. So I might write it as, well, within the subset, it will be proportional. It will be just a certain fixed multiple of these guys. So we can write it as, say, phi of X times epsilon L. Now, to indicate that we are within our small subset lambda, I write here for the factor of proportionality, I write here phi lambda. Let's see what happens if I have an element y that corresponds, okay, here I should have written I, and that holds true for L in lambda. So if y leads to the same solution, so I will get here a factor phi lambda of y, and otherwise the same epsilon L of I. Okay, we are not yet done. Now suppose that L and M are here two subscripts that belong to the same subset lambda. We write for that also L and M are in relation with respect to our partition P. Well, that means that we have alpha L to the x is equal to phi lambda of x epsilon L super I, and alpha M to the x, it belongs, it belongs to the same fixed solution of the in our finitely generated group, so it has the same factor of proportionality. So here we will have phi lambda of x times epsilon M super I. And now similarly I can write down the same thing for the alpha L and alpha M to the y. So I get alpha L to the y is equal to phi lambda of y epsilon L super y, and alpha M to the y is equal to phi lambda of y epsilon M I. Well, let's see. Now let us consider the determinant alpha L to the x, alpha M to the x, alpha L to the y, alpha M to the y. So, okay, this is going to be equal phi lambda of x, epsilon L super I, phi lambda of x epsilon M super I, phi lambda of y epsilon L to the I super I, phi lambda of y epsilon M super I. Okay, what do we get? We just see that here it is obvious that this determinant is equal to 0. Consequently, so if we use that, we see at once that we get so we get for x and y for solutions in SP of our equation 2. For such solutions that come from the same, so which come or which correspond to the same solution of this equation, well, that I have now erased, of, say, over the finitely generated group. So, in my writing with these epsilons, so for any two such solutions, x and y, we get So alpha L to the x, alpha M to the y equals alpha M to the x, alpha L to the y. So on the whole we have alpha L to the x minus y is equal to alpha M to the x minus y. So we can express that in a completely different, not in a completely different way, we can express that in a different way. Let's see. I try now to formulate these considerations in other words, and what we have just seen is the following. So if we have our partition P, we define what I call the relation group for our partition. We define the subgroup G of P, the subgroup of Z to the N, in the following way. G of P consists of the set of Z in Z to the N, satisfying the following relation. Alpha L to the Z equals alpha M to the Z for all pairs L and M with L and M are in relation. In other words, alpha L to the Z equals alpha M to the Z as long as L and M belong to the same short subset of our partition, right? So what have we seen? We had seen here that for two solutions, x and y of this equation here, that lead to the same solution in our finitely generated group, we have this. In other words, two solutions of this equation leading to the same, say, basic solutions of over the finitely generated group. Two such solutions lie in the same coset modulo this relation, what I call the relation group, right? So solutions x and y of, well, that had been equation 2. So of 2p leading to the same, I say, basic solution lie in the same coset mod GP. Now we can the following say, what is the number of basic solutions? Those were the basic solutions, were the solutions that we derived from, well, that was the equation sum L in lambda AL epsilon L equals 0, where we assumed that in this short subsum there is no vanishing subsum, and here we had said that we had C of lambda such solutions. So on the whole we can say, if we take all the subsets of our partition into consideration, we get capital C equals product over all lambda in our partition P, C of lambda solutions. And what we can now say is that the solutions of this equation here, that the solutions in S of P, well, they are just made up of corsets modulo G of P. And how many corsets do we get? We get C times, no, C cosets modulo G of P. And now it is obvious, when we have that our relation group G of P is trivial, so when G of P is just 0, the corsets are just one element sets, so under these circumstances, this equation here has simply C solutions, right? So that is the nicest situation when we have that these groups, the relation groups G of P is trivial. And now, as I see that the time already has advanced a little bit, so after this introduction, I can now just write down a few general results on these equations, and then I will give some more recent results. So, as an application of the periodic subspace theorem, Laurent in 1983 derived the following result. Well, I just quote a simple, his result is more general, and but to state it maybe doesn't make things much clearer right now, so I just state a very special case of it. Let me put it that way. Suppose G of P is equal to 0. So I suppose that we have, well, I have not defined G of P with respect to this equation, but I think it's obvious we just do completely the same thing. We forget about the fact that there is the extra complication with the polynomial factors. The whole definition is just with respect to the exponential function there, so everything is literally the same as what I was explaining. So we suppose now that we have a partition where the relation group is trivial. Then the set of solutions corresponding to our partition P is finite. I can also give a quantitative version of that. Let me see. Okay. Yes. So that is due to Wolfgang Schmidt and myself. That is from 2000. The quantitative version of the same result is as follows, that again, so that is if G of P is equal to 0, then the number of solutions is bounded Okay, I will not write down the result in all details. I said simply bounded in terms of the total degree of the polynomials PL in terms of n, the number of variables, and, well, I have to say, here we had made the assumption that we are working within an algebraic number field. So, algebraic number field. So it is bounded in terms of the degree of the field. Let me say that it would be desirable, that has not yet happened till now, to get rid of here of the dependence of the degree of the field. Then one would have completely uniform bounds, as the other parameters that show up are necessary. That's essentially, if one goes back to the equation over finitely generated group, that's essentially simply the dimension in which we are working, the total degree. So that's nothing else than essentially the number of sums that we have there. Okay. Anyway, that would be a very interesting question to treat here the algebraic case and get rid here on that dependence. Okay, that it's not so easy. Well, let me say, but I'm not going into details here. The case n equals 1, one comes to linear recurrent sequences, and in that case, that is the famous result of Wolfgang Schmidt, and then we have that the multiplicity of linear recurrent sequences is bounded in terms of the order of the sequence only. So in that case, the dependence of the degree has disappeared, and so one has a completely clean result. Anyway, so to conclude, let me just indicate, I see that the time is already very much advanced, so let me just indicate some new result. I will talk on the extension of some old result of Wolfgang Schmidt and mine. Where did the chalk end up? Okay, now I have found it. I had hidden it myself. Okay, so Wolfgang Schmidt and myself in 1993 had considered the following equation: A up to the k plus b uq to the l equals 0, where here un is a non-degenerate linear recurrent sequence, say of all the t, it doesn't matter. So just a recurrent sequence within the complex numbers. We assume that k is less than L, and k and L are sort of natural numbers. They are fixed. Clearly, A and B are some non-zero complex numbers, and we are asking for solutions P, Q within the integers. So our result has been that this equation, call it star. So star has, under these assumptions, only finitely many solutions, PQ in Z2, if the sequence U is not exceptional. If UN is not exceptional, this is characterized in detail. I just indicate one example. We have to avoid, for instance, that our sequence is of the shape f of n times alpha to the n, where alpha is the root of unity. There are other exceptional cases that I'm not going to discuss that. Okay, now what is the extension? I should say that it is clear that natural extensions would be to consider equations of that type in more variables. And indeed, in 2002, in Vienna, there was somebody who had written a PhD on this, treating, that was Mrs. Grünes. So she treated the three variables case. And she has shown that if the characteristic roots of GM, of UN, generate a multiplicative group of rank larger than 1, then again the corresponding three variables equation has only finitely many solutions. And to avoid overtime, I will be very short in giving my result now. So, suppose that the roots of the companion polynomial, so the characteristic roots of the companion polynomial generate a multiplicative subgroup of C star of rank larger than 1, then I simply say the n variables equation has only finitely many solutions. And let me finish by saying that one can even give an example of a rank 1 sequence where the assertion becomes wrong. Consider simply the sequence 1 over alpha to the n plus alpha to the n. It is quite simple to construct for any number of variables an example out of with this sequence where there exists an equation of this type where we get infinitely many solutions. This example works only starting with at least 3 variables. In the 1 variable case, or I have erased it, we had the exceptional examples were slightly different. Anyway, okay, thank you very much.